So I'd like to thank Darren for the introduction and the good work he's done. Let me just emphasize, he's just starting his senior year, and he just started this project in May. So he's come a long way in the last few months. It's been a really fun working with him. So as he talked about, after you've detected an intruder, you might want to know where they are, and that's what this is about. If you can indulge me, I want to take about 30 seconds and let us watch a little bit of George Clooney, and I hope you can hear this. It's better with audio.
By the laser field in the Great Hall.
Aha. The laser fields. Well.
Oh, no. Okay. Wow, that's farther out than I thought. So while this is booting, basically what we're going to do is after we've detected an intruder, we want to find out where they are. So what we're going to do is we're going to take these antennas in the ceiling, and we're going to collect signals that are reflected off from the intruders. So think about that. Someone's walking along, and as they go, the RF signal hits them and bounces off and goes into the receiver. This is a very weak signal, many dB down compared with the direct signal. And we know that's the case because our receivers, our Wi-Fi receivers and so forth, are able to detect without any trouble whatsoever, because the interfering signal in the time-varying channel is weak enough that they just get around that. So this is some work due to another student who just finished his master's degree, Thomas Bradshaw, and we are looking at the tracking problem and doing the Doppler estimation and then the state estimation after that. And I can't hear this. I can hear it. Okay, that of course comes from Ocean's 12, and there's a point there, which is that if you're using other kinds of technology to secure an area, such as laser beams, you're going to have trouble. But RF signals disseminate broadly. You can't dodge an RF signal the way you can a laser, and so you have the opportunity of better security. Wi-Fi is everywhere. You don't have to deploy lasers. You don't have to install switches on your windows. You can just use the Wi-Fi in your house. As Darren talked about, there's two phases. He talked about intrusion. I'm going to talk a little bit about target tracking. And also, as in the case of Darren, this is preliminary in the sense that we're using QPSK. We know in principle how to use Wi-Fi to do this. It's just a matter of doing the deployment. So I want to talk a little bit about the system overview here. Here's a block diagram. So we have a transmitter located at location T1. We have multiple receivers at locations Q1 through QJ. In our case, we had 5 receivers. We have a moving target. We're using digital communication waveforms. And what makes this interesting is each receiver receives a sum of a direct path signal and a reflected path signal. So we're taking into account both of those at every receiver. And so it's like a source separation problem in a sense, but in a little unconventional way. So the processing that's done is at each receiver, separately, it extracts the Doppler frequencies, and then we pass those Doppler frequencies to some central location and use those as an input to a Kalman filter, which then extracts the state information, the position and velocity of the target. What's interesting about doing this with Doppler as opposed to like a time difference of arrival or other kind of geolocation technique is the time synchronization doesn't have to be all that tight. We're not matching down to within a fraction of a phase cycle of the signal. If you're accurate to within probably a few tenths of a second, you're probably going to get a pretty good track out of it. Okay, so here's the block diagram from the point of view of what we did in GNU and what we did not. And pretty much in this prototype, the transmitter and the receiver were in GNU. And at that point, we took the RF signals, brought them into MATLAB. And MATLAB is where we did all the frequency extraction and tracking. Just to show you, kind of motivate that this could work, what I'm portraying here is the equation which relates the Doppler frequency, F sub D, on the track from I to J, transmitter I, receiver J, and it depends, based on the physics of this, on the position of the target and the velocity of the target in a rather complicated way. So what we do is we take that messy equation, we linearize that, and we use that as the observation equation for an extended Kalman filter. And then in our extended Kalman filter, we use a Singer model, which is used for maneuvering targets. So that's sort of down the road. We're not going to say a lot about that, but we had to get that part working. So let me say a little bit about the signal. As I said, we're assuming a botted signal, so we have a time-varying amplitude and phase, which we represent as a sum over some symbol times of a symbol A sub k with a baseband pulse shaping function P of k and a single carrier here. What we're assuming, because we're in a building, the time difference between the direct path and the reflected path is small enough that the baseband pulse shaping function is essentially the same over those time differences. So if we call tau sub ij the direct path delay and tau sub ij tilde the delay on the reflected path, the pulse function is essentially the same over that. And so we can simplify what happens in the signal model. And the basebanded received signal looks something like this. We have two terms. We have a term here corresponding to the direct path with a coefficient alpha sub ij, which is the complex gain on the path from transmitter I to receiver J. And then we have an alpha ij tilde, which is the complex gain on the path from transmitter I to receiver J on the reflected path. And the key concept here, or a key concept, is that the magnitude on the reflected path is much, much smaller than the magnitude on the direct path. By much, much smaller. It could be 10 to 20 dB smaller. Kind of weak signals for us to be doing the signal processing that we're doing. Another term that I took into account explicitly is we wanted to use a different transmitter than receiver. Everything would have been so much easier if I could have used the same transmit clock and receive clock. But looking down to where we're using somebody else's transmitter and our receiver to do all this, we wanted to account for that difference. And in fact, with the GNU hardware, or the EDIS hardware that we were using, especially the older EDIS hardware we were using, this carrier frequency offset was significant. And in fact, that drift in carrier frequency offset is just about the same frequency range as the Doppler we're trying to extract. So we had to work very hard to deal with that as part of our signal processing. So there are two receiver models that we use. In the first place, we took the received data and we ran it into a PLL, where we wanted the PLL to track out the carrier frequency offset. And what was observed, rather perversely and annoyingly, is that the PLL, as it was moving things around trying to track the carrier frequency offset, due to the dynamic and nonlinear nature of the PLL, it actually introduced some frequency components that were the negative of the Doppler frequency that we were after. Well, if you're just trying to do a receiver, you wouldn't notice that. But if you're trying to get the Doppler out later and dealing with this very weak signal, that's a problem. But we still use this because the Doppler components were weak enough that I could take the PLL output and do a reliable symbol detection and get the symbols A sub k out of this. So our other receiver model is, we said, forget about the PLL. Let's not try to track out the carrier frequency offset. Let's just run it through a symbol timing match filter. And in this case, you can model the receiver output as we have the symbol, we have a direct path amplitude, a reflected path amplitude with the Doppler on it, and then this whole thing is spinning around due to the carrier frequency offset. And so we used this signal that we fed into our signal processing in an attempt to try to track the Doppler out. Here's our receiver. We don't have time to say, excuse me, a lot about that, but there's kind of two receive path components that do these two models there. So how do we get the Doppler out? Well, first thing we do, as I said, is we detect the signal A sub k, and we divide that out. I have this symbol I call D2 of k, where I just divide out the symbol. And now we're left with the direct path amplitude, the Doppler amplitude. Again, it's all spinning. And the Doppler component is much, much weaker. So in essence, and taking the carrier frequency offset out, we have a DC component, and then this other component here that's spinning at the Doppler rate. So we took that signal and estimated from that the carrier frequency offset. We tried both DFT-based methods and music-based methods, found that we could make some progress with both of those. For music, we found that if we increased the dimension of the noise space, actually, it worked a lot better, suggesting that it really is not white noise that we're dealing with. So then what we did is we took the carrier frequency offset out, basebanded the signal. That left it with a DC term. We did mean removal, and so now the direct path information is actually gone, and we're left with only the reflected path. And then we did another frequency estimation step to extract the Doppler frequencies. Because of the noise on the system and the weakness on the signal, we had to clean up the Doppler frequency estimate. And so what we did is we took the sequence of frequencies that came out of that and we ran that into a Viterbi algorithm. So we created a trellis where the states of the trellis represent different candidate frequencies, and we had transitions in those frequencies corresponding to movement from one frequency to another. Since physically the Doppler frequencies have to be continuous, that suggested that we're going to have a path through this trellis that wouldn't have a whole lot of motion. And so we set up a Doppler branch cost, which captured the frequency information, and then also a cost associated with moving too far from one frequency bin to another. And then we also implemented a BCJR algorithm on the same idea. And this illustrates a little bit about it. This was actually a situation where the transmit antenna was right there close. We had a good strong signal, not in the ceiling, so it was an early test. But even on this, you can see on the left that on our Doppler trajectory, there's some outlying points there. And then when we ran through the Viterbi algorithm, that trajectory got cleaned up a lot. And so we found that these frequency filtering techniques, we were able to help us do a pretty good job tracking the Doppler, even though it's weak. We ran into some other problems, though. Having done the mean removal to get rid of the carrier frequency offset, that means that there was no 0 hertz signal in the Doppler. And 0 hertz Doppler actually happens. There are a variety of situations where that comes up. So we needed to restore the 0 hertz so that the Viterbi algorithm could be able to effortlessly track through that 0 frequency Doppler state. So to handle that, we created this idea of what's called a balance factor, where we look at the spectral energy on the positive frequencies and the spectral energy on the negative frequencies, and then take a difference and normalize that. And interestingly enough, the balance factor, which sort of represents everything except the one frequency you're looking at, tracks pretty well what the actual spectrum is. So in this plot right here, based on real data, this is a music spectrum underneath, and then the red dots are the balance factor where we scaled that in such a way that it would line up. And you can see that it is actually tracking the same kind of information as the spectrum itself does. So on the basis of that, we could artificially regenerate the 0 hertz frequencies. If the balance factor is near 0, we said, okay, the signal must have been DC or near DC, 0 Doppler. And so we recreated a spectrum by creating a little peak at the origin that we linearly combine with the other spectral points and use that to get just a branch metric, and that is finally then what we used to do our Doppler that we then fed into the extended Kalman filter. Whew. A lot of work to get that working. Okay, you've already seen the map of the building where we tested this out. Here's an example of just the basic Doppler motion. Someone was walking back and forth in the hall of the building, and the Doppler was moving and corresponding to it. You can see the music spectrum and then the peaks of the maximum that we got out of that after the Viterbi tracking. And finally, we have an example of the extracted trajectory. So this is the blue line here shows a trajectory. Someone was walking back and forth in the hall, and this is the trajectory that we extracted from their motion in the hall. So we were able to validate that this thing did the job and works. We've got a lot to do on this. I have some ideas on how to improve the Doppler extraction from these weak signals with a variation on the Viterbi algorithm. The thing we're really interested in doing is extending this to using OFDM transmitted signals to track people using the existing transmitter in the building. Okay. That's it. Any questions?
All right, thank you, Dr. Moon. I see some hands coming up here.
Yeah.
A question right here in the back.
Hi there. And your last slide where you had the extraction of someone going back and forth in the hall.
Yeah.
Did you try to make this person walk straight, or were they swerving? Like, is that a struggle?
Oh, yeah. In fact, I needed to bring this up because that was my second bullet point there. They were walking straight. So what we found, actually, the antennas were spread out. There's more distance in the east-west direction, left to right, and less observability in the north-south direction. So they actually were walking straight. So what we see is, yeah, we don't have perfect Doppler extraction here, and so it is portraying a wandering path here, even though they were not drunk when we did this test.
All right, I saw another. Here we go. Let's get another question over here.
So this is a former student, and he used to work in this building. He knows this building.
Yeah. How do you anticipate this extending to further targets? Do you think the same kind of model would work, or there be too much going on?
You mean multiple targets?
Multiple targets.
Yeah, that actually needs to be a bullet point on the last slide. So if you have multiple targets, then you're going to have multiple pieces of Doppler. And so now it becomes a matter of multiple frequency extraction. We expect it to be complicated, actually, because these signals are so very weak. So if we can get the multiple target extractions and we can do the data association problem, which says this Doppler is associated with this guy and this one's associated with that one, we're going to be great. But you can see that there's some questions there.
All right. Do we have any other questions in the room? All right. Thank you, Dr. Moon.